How you doing today?
Yeah.
Good. Thank you.
Tell us how your day.
It's like the video that I saw today. The teacher goes, students goes, "Can we have a free day today?" No, today was fine. Last week was all my concerts. This week I'm going to Shinedown this weekend. So I'm going to Shinedown. I'm going to the concert for the band Shinedown. No, not going to China. That'd be fun. Like, hey, I'm just weekend trip to China, no big deal. No, Shinedown. Yeah. God, this will probably be my 15th time seeing them. Like that. It's ridiculous. So.
Years ago, I went to a Papa Roach concert. It was like Papa Roach, Hollywood Undead, and
Falling in Reverse and Bad Wolves. Yeah, Falling in Reverse was that. Yeah, I remember that show. All right. So tonight, now it's got to be off track. First thing, your test is in 2 weeks. So your test will be October 8th, I think it is. Wait, not October 8th. Sorry, October 5th.
yeah, I was gonna say maybe.
Yeah, we're all coming on Sunday to do our test. No, the test is October 5th. So I will have your review test for you next Thursday. So when I create up the review test, I basically create up the test to just change 3 numbers on the thing and make up the review test. So they're basically the same thing, just with different numbers. So can take that. You can work on your index card. And then on Tuesday, we'll go through the review test. So you understand how to do it all. You can ask questions on it and everything else. If you think you're great and you don't need to do the review, you don't necessarily have to come to class on that Tuesday. It's just a review. So, and then Thursday is the actual test. You can use both sides as long as it's got to be handwritten, no tapes, no staples, glue, or anything else on it, just handwritten. Unfortunately, there's a class in here until basically 6:45, so we can't get in early. So you'll get the hour and 15 or so to do the test, but I'm going to design it that it should be able to be finished in the hour and 15 minutes, so it shouldn't be too bad. Yes.
Will calculators be allowed?
Yes, you can use calculators on the test, and you're allowed to use your cell phone calculator on the test, if that was your next question. So, like I said, I would suggest downloading the Desmos Scientific Calculator. It works really well, does everything you need on it. So this one will not have nearly as many calculations on it as future tests, but there will be some calculations on it. All right, so tonight, somebody wants to join. Tonight we're going to look at frequency distributions. So frequency distributions are a graphical representation, or not even necessarily graphical, it's use charts. It's a summary of quantitative data. So remember, we've got 2 different types of data, right? We've got qualitative and quantitative. What's the biggest difference between the 2?
Qualitative is describing, and quantitative is related to numbers.
Yes, quantitative is numerical, and those numbers have some meaning to them. Not like a phone number is qualitative, not quantitative, even though it's a number, because it's more descriptive. So yeah, it's a number that has some meaning behind the number. So my wonderful Google AI did this for me today, because I just wanted a random set of numbers and I didn't feel like using the one in the book. So I asked it to give me a list of 30 heart rates, and this is the list it gave me. It actually gave me a list that I had to tell it to put it in a table because it didn't think I wanted a table apparently, but it made me a nice table. So here's a list of 30 heart rates. Is this data quantitative? Yes. Okay, the numbers mean something. We can do calculations with them. That will also mean something. All right. So we're going to take this data and turn it into frequency distributions, and we'll do a whole bunch of stuff with it. So first thing you're going to want to do is write down those numbers. somewhere on a piece of paper or somewhere, because we're going to keep coming back to these, and it's going to be easier if you have them somewhere in front of you. Or take a picture of it with your phone and keep it there. Whatever you want to do to, so you have those numbers. And make it a lot easier than me having to flip back and forth a million times. I'll make it a little bigger, but not much bigger. That's about as big as I can make it for everybody. Can everybody see it? Okay. Oh, shoot. Sorry, wrong screen. This is the one I wanted before. I have two screens of literally the exact same stuff, so I can actually go ahead and write things before you actually see it. All right. Almost. I see a couple of people still writing. You good? Okay. All right. So, everybody got enough? Okay. To create a frequency distribution, there's a few steps we have to do. The first thing we have to do is we have to figure out the range of the data. Because when we're creating this, we're looking at making it only for the data that we have. So how do we find the range of that list? Right, so what's the smallest number here? I should have told Google to put it in order for me. So 64 looks like the smallest. And the highest is an 82. Oh, there's 82. All right, so we got 64 minus 82, or 82 minus 64. So 82 minus 64. So my range is 16? No, 18. All right, so that's step one. We need to figure out the range. We got that. It's 18. So we took the lowest and the highest. The next step, we want to figure out how many groups we want. So last class, we called these classes. So how many classes do we want? All right, so how many groups do we want to break these down into? So it doesn't make a difference. I could say 18 groups if I really wanted to. Not as helpful. So let's break this down into 6 groups. Sometimes they'll tell you how many groups they want it broken down to do. Sometimes they won't. Sometimes you just get to figure out which one you want. You're going to see in the next step why I chose 6. So the classes is just something either they're going to tell you or you're going to have to pick based on the data that you have. You don't want too few classes because then all the numbers are grumped up together and it really doesn't help you. And you don't want too many because then everything's going to basically be ones and that's not very helpful either. Once you've determined how many classes there are, we need to figure out the class width. To do that, you divide the range by the classes. So I chose 6 classes, so my class width is 18 divided by 6. So my class widths are 3. All right. That steps all make sense? Good. Now, we have to make our classes. So you're going to start off at the smallest number, and we're working in groups of 3. So my first class, the range was 64, right? So we're 64. So 64, 65, and 66. Yes.
I don't know if I missed anything, but why is it 64 minus 66?
Oh, no, it's not 64 minus 66. It's 64 to 66.
Oh, okay.
Because we're basically, again, we want to get we have a range of 18. We want 6 groups equally spaced. So then it's 67 to 69, 70 to 72, 73 to 75, 76 to 78, and 79 to 82, because I'm off by 1. When you're creating your class, you want to make sure that each class there's no overlap, and that every number has a place to go. Okay? So there's no overlap, and every number has a place to go. Yes.
Class width is basically the range.
Yeah. How far? Yeah. Yes.
Why is it going up 2 numbers per class?
It's actually going up 3 numbers per class.
Oh,
64, 65, 66.
oh,
It's okay. It's one of those things, like it's the matter of where you're starting to where you're going. And one of the things that we're going to look at a little later in class, when we start talking about histograms and things, is that you typically do not want to use the numbers that are there. Why is the last one 3? Go ahead, ask your question.
What? 4, 79, 80, 81, 82. Why is the last one 4? Or does it just not matter? You just whatever.
79, 80, 81. Right. So I needed the extra number because I needed because you have to have them all. And I didn't want another class with just 82.
Because you picked 6 classes.
Yeah.
Shove them all.
Yeah.
Okay, that makes sense.
Yeah. That happens sometimes when you're looking at them. Like so we could have made another class and just did it 82 through the next number up, which happens sometimes. So it just depends on how you want to space out your numbers. We could have done 64 to 67, 68 to 6. It could have done it that way, and my last class would have been a little higher. So it just depends on how you want to do it and break it down so that they're all there. You don't want your things going, this one I have 5, this one I have 2, this one I have 6, like that, because then the data is not really useful in that case. All right. Now that we got our classes set, we're going to set up our tallies. We're basically going to tally up the numbers. So This is where you guys come into play because I don't have that number on my screen. How many numbers are there between 64? I know how many total numbers are. There's 30. So when we get to the end, there better be 30 tally marks. There's 5 for the first one. Okay. How many 67 to 69? Five there too. Okay. 70 to 72. 5. 73 to 75. God, I hate the AI. 76 to 78. Let me guess, it's 5. Oh, it's 4? 79 to 82. Okay. The funny part about it is I looked at the list and I'm like, that seems pretty random. There's multiple numbers in there. Some numbers repeat. Really, Google? All right. It's fine. It's not the end of the world. That's a frequency table. All right. When we're looking at creating them, that's in essence what a frequency table would be created as. Okay. It's designed to tell you how much is in each of the classes. And now I'm going to go to the book and I'm going to grab theirs so you can see a little bit of a different frequency table since I apparently didn't tell the AI to randomize the numbers a little better.
You're so proud of yourself. Sam.
I know, like, and oh well. It was like it was easy. Now I know why it was easy. All right. Because the problem is that if I ever asked you guys to come up with random numbers, you guys can't do it. It's almost impossible to come up with a truly randomized set of numbers because you have numbers you like. And those numbers will continue to come up within your things. So it's really hard to actually make a true random list. There's ways to use computers to do it. And normally I do, but I didn't do it today because I wanted to play with Google's AI. So here is the actual problem that was in the book of 50 heart rates. And they did class widths of 10. And they did 5 classes. And they counted them up, and that's what they got as their frequency distribution. Okay. So 2, 10, 32, 5, and 1. It didn't tell me what they were doing. It doesn't say it's necessarily resting or whatever else. It's just these are their heart rates at that time they took them. Some teachers, like when they actually teach this, like, and I have an actual class that can do this, and they have a lot more time, like in high school or middle school, they'll actually give people like the things that have the kids test their heart rates and stuff like that in class, and then they'll exercise and test them again and see how things change and those type of stuff. So, all right. So that is a frequency chart. That's literally all a frequency chart is, or frequency distribution. Okay. But what are some of the things that we can now look at this and figure out? Yeah.
What the highest and lowest are in the range.
Yeah. So where's the majority of them?
Oh, no, 77, 86.
Yeah, 77 to 86. Basically right in the middle, right? That's what you were going for, I know. So also, what do you notice about the symmetry of the data? Is it kind of symmetric? Or is it skewed one way or the other? Now I'm asking big words that I haven't actually talked about yet. Which way? Low or high? Well, if you're going to say it's skewed, I'd say it's skewed low because there's more numbers down low than there is up high. I would actually say this one's pretty symmetrical. Like, it's not horribly off. Like, when you say it's skewed, the 32 probably would have been down there, and that would have been 10, and there would have been like very few numbers up on top. But when it's skewed, it's going to be really skewed. This one's kind of symmetrical. Maybe a little skewed low, but nothing drastic there. All right, two other things we're going to look at. Two other terms you need to know. Neither one of them are crazy hard. We talked about relative values last class. We were talking about relative, we were counting up how many there are, and we were dividing them. Relative frequency is the exact same thing in my frequency chart. So there is the relative frequency. All it is then you just take the frequency and divide it by how many total you have. And since my data was all basically the exact same, I might as well use the books one, which I was trying to avoid.
The number of observations, what?
It's the number in the class divided by the total number of observations. So in this case, the first one, the class was 2 divided by 50, which gives you the 0.04, 4%. 32 divided by 50 is the 0.64%, or 0.64 or 64%. We also can do what's known as cumulative charts. What do you think would make it a cumulative chart? So in essence, the difference is you're going to add the pieces together as you go up. So my frequency is 2, 10, 32, 5, 1. The cumulative frequency is 2, 12, 44, 49, 50. You're just adding them as you go up. Yes. Sure. Word what? Oh, I moved it. Because it literally just said add them up as you went on.
Oh.
Do you understand what the word cumulative means? That's literally what the definition was. And it was one of those ones I'm like, I'm pretty sure they're going to get what cumulative means. So yeah, you don't need the exact definition. There was no formula or anything else to it. You were just adding them up. The relative frequency, there's a formula to it, so I figured I'd have that up there. So cumulative frequency is just a frequency chart and a column adding them up as you go. This is useful if you want to say, like, how far are they between it? Like, how much is between 67 and 96? You can just subtract those two numbers to find the answer. That would find it out for you. You also, cumulative frequency helps out make sure that you didn't miss any, because your final one should be 50 in this case, because there was 50 values. Or if it was the cumulative relative frequency, it should be 1, because that's the total percentage. One thing, and I snagged 2 people on Facebook this week with this. When you're writing your numbers, don't put percents after those. It's not 0.04%. It's 0.04 or 4%. Okay? Don't put the percent after the one you put the decimal in. Okay? Because that then moves the decimal 2 more places. So, all right. So just the little things can make a very big difference. And those are the types of things that when you start talking about numbers, like, you know it's 4%. Like, we do that change right in our head and not even think about it. But if you put the percent symbol after it, it changes its meaning, which then could cause other problems with how people interpret things. So just keep those things in mind. All right. I want to do that one. Let's see. All right. Not that yet. Actually, you know what? Yeah, we're just going to do that. All right. Let's go into histograms. All right. A histogram. So this is actually the exact same data we just saw. But there's a couple very important things that are different about it. So a histogram, first off, that's not a bar graph, even though it looks like a bar graph. Okay. A bar graph can be used for qualitative data or quantitative data. And actually, one of the biggest differences between this and a bar graph is they touch. Bar graphs are not supposed to touch because it's just like the thing with the points in a line. When they touch, it means there's nothing between those values. Okay, it means it's a continuous stretch. So a histogram they touch because it's continuous. A histogram can only be used with quantitative data. Right? It is a reflection of that frequency or relative frequency distribution that we just did. Let me actually pull back up the table because I want you to see something. So this was my table. All right, so that's the table. And that's the histogram for that table. What are some things you notice about them? There's one big thing. What's the first class in the table?
57.
57 to 66. Right. Why? What would be, if we started at 57, what would be the next number that I would put? 66 or 67?
66.
So then where is 66 going? Is it going in the first one or the second one? See the problem? So when I'm putting my numbers down the bottom, if that was 66, is 66 here or here? I don't know. If I put 67, is 67 here or here? I don't know. Makes a problem. So we always list our histograms in decimal. It's always half, whatever it happens to be. This way, I know in this box here is between 56.5 and 66.5, but the 0.5s don't exist in my data. So these are all the numbers from 57 to 66. These are all the numbers from 67 to 76. Okay? That's why they can touch, because at that point doesn't actually exist in the data, but it could because these are continuous values. Okay? If I had decimals in my problem, I would just go one more place. So if it was, say I had numbers that were 66.1, I would just do 0.5 after that point. So it would be the 0.05 or 0.15, whatever it happens to be breakdown. You just add the half to whatever the piece that you're looking at. Okay? So that's the biggest difference between a histogram and your bar charts is they touch and the classes are broken down that way. Other than that, it's just straightforward, just putting the numbers in the columns. And your frequency should be broken down evenly going up. So these are by fives. No big jumps, no breaks, because that would cause your data not to look accurate. Can everybody still see? Are we good with the light? Okay, then I will leave it this way. As the sun went down, so it got a little darker. All right. The other thing we're looking at, now you can start to look at this chart and see what I was talking about earlier, where it kind of looks symmetric. It has that kind of a nice little hump to it, a little bar graph or bell curve thing that you're going to see a ton going forward. When we're looking at skewed data, this is what you'd see. If it's skewed, it's non-symmetrical, obviously. If it's skewed to the right, the hump is to the what? To the left. If it's skewed to the left, the hump is to the right. Now, the question is why? Why would we say it opposite of where it is? Yes. Yes. It's really, if it's purely symmetrical, your mean and median will be in the middle. Will be exactly the same. They'll be right in the middle. If I looked at, remember, median tells you it's exactly half on both sides, right? So my median in this one will be probably right about there. Maybe a little over. However, these values over here are going to pull my mean to the right. That's what's meant by skewing right. Same concept here. If my median's here, my mean is going to be over here, which is being pulled left because of the values down here. Those outliers are going to pull it in the direction. Okay. So skewed right means my mean is being pulled to the right of my median. Skewed left means my mean is being pulled to the left of my median. Okay. So it's not where the hump is. It's actually where the tail is the way that you want to look at it. Okay. Really easy to screw that up.
What's the circle part again?
That's what's pulling it. That's the tail.
So, okay. I'm confusing what I remember.
Okay. I want you to remember. Hold on. Let me get rid of the circles because the circles really aren't that important. I want you to remember skewed right and skewed left. So skewed right means that the mean is being pulled to the right by those outliers, those pieces at the end. That's what I was circling. So that's what's pulling it, pulling the mean to the right. Skewed left means the opposite. It means those values in the low end is pulling the mean to the lower end. Okay. So remember at the beginning we were talking about home prices and stuff in Connecticut? The wealthy areas down in the southwestern part of the state is pulling the mean higher. So our housing prices would be skewed to the right because our median's not that high, but our average or our mean is a lot higher than that because of those high price value houses there. Okay. Where if you looked at an urban setting where you have a lot of more lower end houses, but you might have some upper houses, the median might be a little higher, but those really low value houses are going to pull it down, which is going to skew it to the left. Because it's going to pull the high, most of the houses are up here, but those low value houses are going to pull it the other direction. Does that make sense? All right, let's look at one. find one. I want one with actual numbers up. It's hard to. Yeah, I'm trying to see if I can find one with actual data. Perfect. No. All right, let's look at this one. All right. So here, this is income in the United States. Okay. So if we look at this, you've got your hump and then a little tail at the end, right? Okay. So if I was going to add up all these values and find the mean or the average, these values over here are going to make it higher. Okay. So it's pulling my mean to the right. So it's skewed right. Yes, no? Okay. I figured with actual values, it might make a little more sense.
I feel like I have questions, but I don't even know how.
Well, if it comes up in a few minutes, just tell me that.
Okay, so just to confirm, like you have to have those numbers that are at either the bottom or the top to skew something.
Well, no, you can any graph. You can tell any graph. It doesn't necessarily have to have the numbers, as long as it looks.
Those percentages at the end are what's skewed or not.
Yeah, the values at the end is what's skewing it. It's pulling it that direction. Yes. So I don't necessarily have to have numbers, but the numbers are what's going to actually do the skew. The point is, when you're looking at it, though, you should be able to look at a graph and be able to tell if it's skewed one way or the other. Okay? Because a perfectly symmetrical graph looks like this. I'll just use this one. Sorry, I'm just literally copying images off of Google at this point, which is fine. That's how this works out nicely. So this is perfectly symmetrical, where my mean and my median are basically right in the middle. The data on either side is exactly the same, so therefore, if I was going to add them all up, they'd balance out. It'd be right in the middle. Okay? So when I have those tails, when I have those outliers or those values on the extreme ends, it's going to pull that mean towards those. And the more outrageous those numbers, and the further that mean gets pulled. Okay. All right. I wanted to actually do one. Let's see if I can find the data real quick. And it's not going to let me. All right, that's fine. All right. Another way. Oh, sorry. Wrong side. That side. Yeah. Has anybody ever seen a stem and leaf plot? All right.
Can I ask you a question?
No. Just kidding. Yes.
I'm being realistic with you. I'm here because of my degree.
Yep. I
I
know.
have no freaking clue where and when and how I'm going to use this in my life.
What's your degree?
Nothing.
So
I can get it. Like you're going to look at statistical stuff of diseases and all, but
No. You're not.
use this.
No, you're not going to do that. Your health, what is it, health management and stuff like that?
Yeah.
Okay. Right. So one of the things that you could use this data, like this type of stuff for, is for scheduling. It's very important. Figuring out when people are going to be on in that hospital, what is your busiest times, those type of stuff. That's what these charts would be useful for. So you could take all of your data, for the last month, you could take all of your the number of patients that you had in your thing and everything else, and break it down and go, okay, we average this many patients on a daily basis. So I need to plan for this. However, I know that this is going to be skewed to the right. So the majority of the days are there. However, I have some days on the weekends and stuff like that that get really busy. So I need to somehow plan for those while still maintaining a decent schedule. So they use this type of stuff to be able to plan those things and figure that stuff out. So I don't know, like, it's one of those things, like, depending on how far you go in that and what type of positions you're in, those type of things, depending on how much you're going to be doing that type of stuff. But it can come up. So that's why it's there. I'll tell you right now, the reason statistics was chosen, the health fields needed a math class. Period. Every major, even if you're an English major majoring in poetry, you have to take a math class. It's one of the distribution requirements. It's like a math teacher had to take an English class.
When they earn, now it's 3. It's 1 and 2 in healthcare statistics.
Right. So you take a whole bunch of statistics. It should have, before it was algebra, there was 2 algebras and a statistic. So they got rid of the algebras because you really didn't need that as much. They know that the data science and everything else really flows into the statistics ends. That's why they put those in there. So is everything going to be useful? No. But I would be willing to bet this is more useful than you learning how to solve for X. So we'll go with that direction for a little bit. And yes, I probably can come up with an example for most things. This is what happens when I taught high school for 24 years and kids constantly ask me, when am I ever going to use this? And I can come up with an example. So has anybody in here seen a stem and leaf plot before? Okay, so one of you. All right, so a stem and leaf plot actually is a frequency distribution, a very specific frequency distribution. Okay, a stem and leaf plot groups your classes in groups of 10 based on the leading number. So here are some values. Okay, so I've got 97, 99, 108, 110, and 111. Okay, those are my data points. So those 5 points. If I wanted to put those in a frequency table, I can break them down by 10. So I'm going to take all the 90, and put them together. So 90 to 99 is going to be one class. 100 to 109 is going to be a second class. 110 to 119 will be a third class. That's what this is. So my 90s class, I have 2. My 100s class, I have 1. My 110s class, I have 2.
Oh,
It's just an easy way to break down your frequencies.
So does P mean multiply by 10?
No,
No.
that's the numbers in front.
no, because you said it'll always be 10 in groups of 10.
Right. So this first stem is my 90s. So my numbers were 97 and 99. I have 2 in that class. Okay. So if I was going to write this as a class like I did before, I would have wrote it like this. I'd have gone. I'd have gone 90 to 99 and 2. 100 to 109, 1. 110 to 119, 2. That would have been a frequency chart, right? Okay. The stem and leaf plot does both those put together. Basically, what it's doing is it's giving me all the data and showing me my frequency. So this right here is 97 and 99. In essence, the first number is my 10th place, And then the number in the leaf is my ones. So I can look, I have 97 and 99. The next one right here, I have 108. Here, I have 100 or 110. And then if I use that one, I have 111. So it does two things for me. One, it helps me organize my data. Two, it puts it into classes so I then can look at it in terms of classes. And you can break down your leaves to do by fives, you can do it by tens, you can do it by hundreds. It doesn't make a difference how you, it just depends on your data. Okay? So, no, what I'm saying, you could pick. 10 is the default. 10 is what is normally used. However, if all my data is in the thousands, I might want to make it the first ones of the all hundreds, and then the last digits afterwards. Or I might make them, it'd be, so for 1,000, it might be 10 and 54 and 55 and 56, whatever. And it'd be 1,054, 1,056. So you can set the stem and the leaf to break those numbers apart in a way that you want. The default typically is 10 though, because it's the tens place or whatever is after that, and then the ones place is my leaf. Okay. The nice thing about it is it allows you to then take that data. Remember how at the beginning I had to count up all the numbers? If we did this at the beginning, you'd have just listed those numbers as leaves and then go, okay, I got 5. Okay, I got 6. Or okay, I got 4. It's like you'd have had it done already. You wouldn't have had to go through and count how many you had because the leaf would have given it to you for you. So the stem and leaf plot's a way to organize your data and then use that data to do a frequency distribution, a histogram, or anything else after it that you want. Okay? So while it looks crazy, it actually is very helpful in the design of it. So let me actually show you another one of these. Yes, go ahead.
I said it makes a lot of sense once you know what it is.
Yes, that's the thing. It's like if you don't know what it is, it looks crazy. It's like, what on
Here,
earth
I
is
thought it
that?
was 7.9 and like 0.1.
No.
So I was like, I didn't know what was happening.
Yeah.
That makes a lot more sense.
Yes.
The 8 equals 108. Use that for like other numbers, like you 11 equals 1.
No. So the 8 didn't equal 108. The 8 in the leaf, so this leaf right here is 108 because it's 108.
Yeah, I'm just wondering, does that have to be like the middle, or can you like 1 equals 11?
Oh no, they just used that one to show you what it meant.
Oh, okay.
So like you could have done 11 and then this would have been 0 would have been 110, which is what you're going to see in the next slide that I'm about to put up. We're going to do sports, even though I know none of you like sports. All right. Please tell me you guys know who Babe Ruth and Barry Bonds are. Okay. Okay. Both major home run hitters. All right. So this is a stem and leaf plot. This has 2 stem and leaf plots. Okay, put together so we can use some comparison. All right. So let's go through and we're going to look at the Ruth side. All right. So this first set of things right here, he had 0 home runs, 4 home runs. Who's that over again? Over the side. So he had 0, 4, 3, 2, and 6 home runs. The next one, he had 11 home runs. The next one, he had 29, 25, and 22 home runs. See how I'm getting the numbers from the stem and the leaf? 29. No, so this is my stem. That's the stem. This one's a little more confusing because it's doubled. Yeah, This one's doubled. There's two things because we're looking at two different sides and comparing. Yes. Yeah. So if you ignored Ruth altogether, the bond side would be normal stem and leaf plat where it was the stem and then the leaf was on the right-hand side. Okay. But in this case, my stem is in the middle because I have two sets of data that I'm looking at. These are home runs. How many home runs I had? Okay. But the question is, do you understand how I'm getting those numbers there? Okay. Because that's important to understand for that. That means you understand how a stem and leaf works, believe it or not. And purely that's it. And then if I wanted to look on this side, so Barry Bonds had no 50 home run seasons, no 60 home run seasons, and he had a 73 home run season. He also had a 46, a 42, a 40, a 49, a 46, and a 45 home run season. This is why everybody claims he was on steroids, because he went ballistic and hit a ton of home runs that season. So, all right. So, but that's how a stem and leaf works. Yes.
What decides the order of the numbers in the leaf?
Normally, you put them in order from numerical order. This one is done by season. So his first season, he hit no home runs. His second season, he hit 4 home runs. Third, that's how they actually organized it.
You see something like this with the column with only one number in it, majority of the time.
Is your stuff. Yes. Because your data, you should have more than one data point. The other thing is, like, if you went the other direction, it wouldn't make sense because now I have a bunch of different stems with the same leaf, and that wouldn't help me organize my data. Okay.
Like groups, data, because it's not like skewed right or symmetrical. It's just kind of everywhere.
It's kind of everywhere. There's no real symmetry or anything else to it. So it doesn't necessarily have to be skewed right or skewed left. So
Versus on it's skewed left.
yeah. Because it's there and this one's pulling it higher. Yeah.
Are you
Oh, sorry. Skewed right. Sorry. It's the way I'm looking at it because it's down. It's skewed right. Yes. Yes. Because if I did it this way, yeah, it's skewed right. I wasn't even thinking of that when I was looking at this chart. So when you asked me, wait. Neither do I, so it's fine. Yes.
Will we ever have to identify which way it's skewed sideways?
No, you will not. That's why I didn't ask that question in this one. All right, so a stem and leaf plat is just a way to organize your data. And then you can use that to create histograms and everything else from that. All right. It also, depending on the data you're looking at, this one doesn't. It also can help you look for symmetry and those type of things as well. So not this one. A chart that a lot better helps you organize and look for symmetry and stuff like that are known as dot plots. So this is another one that it sounds great. This is what a dot plot is. It's literally a number line with dots on it. Okay. This one is all the wins by the Chicago Cubs. So, and they broke it down by groups of 2. But their points are every point. So there is a dot for every single data point. Okay. So remember how we were talking about classes before? I said when you have too few or too many, it causes you to like not really organize the data much. In the stem and leaf plot, our classes are basically a size of 10. And then we have as many classes as we have the data. In this, my class size is 1. Every data point's its own individual place. Okay? So that's how you have so many points on there. And the only reason we have stacked ones is because those numbers of wins happen multiple times. All right. because of the essence of the nature of winds in a baseball season, you do see some clumping, typically towards the middle of the thing, right around 80. 81 is the halfway point of the season, so right around there is when you see the majority of the points. But you can start to see that spread value too. But that's all a dot plot is. I'm never going to have you make a dot plot. But again, it's another way to organize your data. These type of graphs, a lot of them, when you have a bunch of data points, you're going to use a computer to organize and create the graph. Actually, 99% of the time when you're going to create a graph, you're going to use a computer to create the graph. Because why not? We have computers. Use them. But knowing what they are and what they mean is the important piece. So that's why we're showing you these. So this is a dot plot. It's literally just a bunch of points. Simple, straightforward. All right, last one. One of the very cool things that we can do because of computers is we can create cool graphs like this. This is what's known as a geospatial graph. And this one specifically is called, hold on. This type of graph actually has a very specific name, but I didn't remember it. So geospatial graphs are anything using geography and those type of things to be able to break out information. So these are called, I'm totally going to chop the name of it. That's why I literally didn't remember the name. So this specific graph is called that. Don't ask me why. I don't know how they came up with that name for it. So this graph right here represents the population in county everywhere in the United States. So you can start to see the darker colors are where the majority of the population, the larger counties are, the bigger the population. So down here, California, Florida, the Northeast is a little dark, like lighter blue, but nowhere near as empty as the middle is. Yes. Oh, it's just because I clicked a county when I was copying the graph. Okay. So ignore the little red dot in the middle. This actually, you can go to the census.gov, and you actually can create these graphs from any data you want. You can tell it how much you want it broken down, and it'll create you actually one of these cool graphs. I literally did this afternoon. It was actually really kind of cool. Where you saw this graph was where one of the places that you've really seen this graph is here. Let me actually find it. So one of the things that they always kept putting out was the presidential elections. And they put out this graph. No, not the electoral votes, actually. So the electoral votes is actually kind of easy to recognize. It's like, it's just by state, which, while being annoying, is what it is. At some point, I might explain to you why you really don't want a popular vote system, because it would just make things worse. This graph. So, who won the election? Actually, this is from 2016, so this one actually was Trump. But if you look at 2020, the graph actually looks very similar. Okay, because the majority of the country, when you're looking at it by county, leans Republican. However, our population, which you just looked at, is here here, and up there. That's where our population centers are. So the majority of the people are in those blue areas. So while the country as a whole, like if you look at each individual county, would vote that way, those blue areas have a lot more population that move the popular vote one direction. So that's where people have seen this graph before, is like typically like this. Or what you've most recently seen it, they showed the COVID numbers on these type of graphs when they were looking at it by infection rate by county through the United States. They actually had shown a lot of these types of graphs to show where the hot spots were. And the hot spots were, guess what? Where the population centers were. Southern Florida, California, the Northeast. That's where everybody's population is. So when you're looking at a lot of those graphs, especially these types of graphs, you have to understand where the population is, because that does skew the look of those graphs. So, all right. But these are kind of cool graphs. Actually, there's one other graph that they had on here. Actually, let me go to the 2020 election. Yeah, the 2020 election one actually is better. There was a really cool one, but hold on, let me look at the 2020. And whatever anybody says, Wikipedia's actual information is pretty accurate nowadays. They always want money. All right, so here is that same graph that we just looked at. This is the 2020 election. Notice it didn't change by much. Honestly, this was the biggest change. Yeah, and this was mostly red last time, so that changed a little bit, and there was more blue down through here. But for the most part, if you look at it, it still looks the majority is red. There's just nobody living in the middle. This is a really cool graph, though. So that's if all the counties were scaled by population. Right. So you can start to see the big population areas, and that's where you get your blues from. Now, if we went to a purely popular vote thing, they would literally campaign here and in New York. Nobody else in the country would see the president, because it didn't matter. You win the population here, and maybe a little in Southern Florida, you win. So as much as everybody hates the Electoral College, it was designed to spread out the votes so that even the smaller states have some say in what goes on. But yeah, these are some of the cool visuals that you can start to see now when you're looking at data. But they all come from those basic ones that we looked at before with the frequency tables and stuff like that. So, all right. Questions? Okay, so we're now through 3-4. So we did 3-3 and 3-4 tonight. So we've got 6 sections to go and 3 classes left. Have a good night. You too. You too.
Which ones do you want us to do? The rest of 3?
You should be able to finish through 3-4. So we still got 3-5 to go. Have a good night.